Okay, then welcome everybody to the 16th session of FSTA. And it is my pleasure to be the chairman. So this would be kind of a continuation, but a scientific continuation of yesterday's show. And the first talk would be by Manuel Ojeda Hernandez. And the title of the talk is not this one. A characterization of direct systems of credit attribute implications.
Thank you very much for the introduction. Thank you very much for this. So this will be a sort of scientific karaoke. I will have the lyrics here, but uh, uh, I will also try to not read as much. So this is some joint work I'm doing with Domingo López Rodriguez, also from the University of Malaga. And the idea is to work on fuzzy formal concept analysis, and the motivation comes from two very common lines of work when we're doing systems of attribute implications. And the problem is that we want to make the computation of closures as efficient as possible. So there are two main lines of work. We can minimize the size of the system of implications so that the closure, which is an iterative procedure, is cheaper, or we can find the algebraic conditions so that the closure is found in only one iteration. So this is the motivation. This line of work I tried to solve during my PhD in the fuzzy setting, and is still ongoing, not the PhD, but the research. And this talk will be about finding direct systems in the fuzzy setting. So some basics. I'm going to work in the framework of fuzzy formal concept analysis. So we have a formal context, which is a triple GMI, objects, attributes, and a relation. And this relation is a fuzzy one. So it goes from the Cartesian product to some complete residuated lattice of truth values. An attribute implication is an expression like this between two fuzzy sets of attributes. And with this, we can reason, we can do logic. So there's a fuzzy attribute simplification logic that was developed some years ago by the group of Malaga, by the group of Olomouc. And we have some axioms and derivation rules that work with it. And this is related, like the axioms and derivation rules of this logic will play an important role in finding direct systems of implications in the fuzzy setting. So how are things in the case? Given a system of implications, we can compute the closure of a set, of an attributes set, like this. This operator is done, but this operator is not a closure operator. It's a pre-closure operator. It's inflationary, it's isotone, but it's not idempotent. So we iterate it until we find a fixed point. And this normally finite, because we're dealing with computation, so it's normally finite, but in any case, even in the transfinite case, we find this operator, which is indeed a closure operator. And we say that a system is direct if doing the pi operator once coincides with the phi operator. So if pi is idempotent just in the first iteration. So even though these systems are larger in general, the computation is much faster. So because we only need one iteration. So this would be helpful for example, recommender systems where the knowledge base is fixed, and we will do a lot of recommendations by computing closures. So as an example, maybe the video recommending algorithm in YouTube. Every user of YouTube is recommended videos. So these are many recommendations that have to be done dealing with the same knowledge base. And why do we go to fuzzy? Because liking or not liking a video is just one value, but when you have a 5-star range of punctuation, then you're automatically in a many valued setting. So in this work, we will assume that L, the lattice of truth values, is a finite chain, and the pi operator in the fuzzy setting is defined like this. This was done way before me, so yeah, this is just background knowledge that the pi operator is defined like this. Again, this is inflationary and isotone, but not idempotent, so we need to iterate it to find the phi operator, which is indeed a closure operator. And it stands to reason that our direct system in the fuzzy case will be any implicational system where phi coincides with pi for all sets of attributes. So the definition was easy, following the inspiration of the classical case, but let's find the algebraic characterization of a direct system. So again, following the suit of the crisp case, we extended the so-called exchange condition to a fuzzy condition. And whenever these conditions are met and this implication that satisfies this exists, then we say that a system is direct if and only if it satisfies the fuzzy exchange condition. And well, the proof, on one side is just following the fuzzy attribute simplification logic axioms, and on the other hand, for the converse implication, there's some metric that goes monotonically down. So in a finite number of steps, we find 0. So it implies directness. And the main point here is that if since we have an equivalence, logical equivalence, it's a if and only if the fuzzy exchange condition is not met, it means that we lack an implication. So how to make a direct system of implications? Well, we have an algebraic condition that tells you when you are missing one implication. The direct algorithm would be, okay, you don't have this implication, add it. And that's exactly the point. Knowing that this exchange condition fails is not just an existential thing, but a determining thing. So it's not just some implication is missing, but we can find exactly one implication that is missing, and this inspires the algorithm that if we have a system of implications, we will check the exchange condition. If it's met, we have a direct system. If it's not met, we have found an implication that is missing and we add it. And we repeat this process until we get a fixed point. And from every system of implications, we can get a direct system of implications. These are some sketches of the algorithms. So the idea, just take two truth values, check the conditions. This is just checking the conditions of the exchange condition. And if we get an implication that doesn't meet the criteria, then we add it. And we combine it so that it's not too redundant. So we simplified using the simplification logic axioms. And this algorithm is indeed correct, and that's what we want to do. So it terminates, it's correct, and the logical system that we get from the implications is the same, so we're not adding or missing information. You can find at this website a detailed trace of the algorithm in an actual example, but it would be too long for the presentation. So what was the idea? The idea has been to extend the notion of direct implicational system to the fuzzy setting. We have reached a definition that we're happy with. We have also characterized algebraically the conditions for a system to be direct, and we have developed an iterative algorithm that will transform any implicational system to a direct one. Some lines of future work. This algorithm still needs to be studied theoretically from a computational point of view. So this is still not done. And it would be nice to combine the two lines of work that I said at the beginning, small direct systems and direct systems that reduce the number of iterations. If we have the smallest possible system that is direct, then we would have the shortest computation time for computing closures. And this is what I wanted to tell you. Thank you very much.
I did not quite catch why your system converges. Yeah, I mean, why when you add implications, yeah, then finally you should stop. Yeah, I understood that this is the property of this direct system, perhaps. Yeah.
Yes.
However, it requires checking. Yeah. So something, yeah, in this direction. Yeah, I didn't quite understand. Yeah.
Okay. So
why it works.
why adding these implications will converge to a fixed point? Yes. This algorithm creates a monotonically increasing sequence in a finite space. So it will necessarily converge. Yes, finiteness is the reason. Since we are orienting these to computation, everything is finite. For now, yes, we already have an improved version, which is a bit more specific. Yeah, it's more intelligent strategy, but this was a bit of a brute force effort, and uh, but it does work, and it's reasonably quick. Thank you for your question.
Okay. And as a second question, Bernard?
I have two, but the second one was the same as Irina, so I have only one. In you go to residuated chain, in fact. Yes, in
Yes.
your example.
Yes.
And we had one in the previous lecture also. Yeah. Using Gödel, you can do that.
Yes.
But that's not my favorite operation because it doesn't create any new values. Suppose, well, do you have first a way of choosing the T norm with a certain
Yeah, yeah, yeah.
semantics, with a certain semantics? You know, if
we can put any T norm in the algorithm, it's not Gödel necessarily, but it must.
no, but you have some T norm. Huh?
Yes.
Yeah.
We choose the T norm.
Yeah. So do you have always we hear, oh, you can choose any, there's a lot of freedom of choice and you will ask the expert. So you're the expert now.
I am the expert.
Yes. But do we have any ways of choosing that T norm with the proper semantics? Because semantics is very important in
In the applied field, like
I guess
going
you
to-
do this for using it, yes?
yes,
Yeah.
that's the idea.
Yeah.
But I'm not the user, so
Uh-huh.
we did the experiment with both Gödel and Lukasiewicz T norms. Any T norm could be used that works in a finite chain, so not product, obviously, but it's just a theoretical approach. So I don't know which T norm is it.
This is the second part of my question, which is
Yes.
interesting because it reminds me of how we computed transitive closures, and we have quite some
Mhm.
format algorithms there like 20 years ago. If you do it for a certain T norm, does it save you time when you do it for a bigger one?
Oh, that's a very interesting question. I don't have the answer right now,
Might be the case.
but thank you for the question because it's something to look at. Yes, thank you.
If there are no any other question or comment, let's thank again the speaker. Thank you. And our next speaker would be Lubomir Antoni, which is going to talk about distance functions between closure systems and their connections, again, with the fuzzy formal concept analysis.
Thank you very much for introduction. I am very glad that we can be here together with Andrej Kridlo at this conference with very friendly atmosphere. And we would like to present our results, which we obtained during our regular seminar meetings at our university. But this work is joined not only by university, but also by Slovak Academy of Sciences and also with Palacký University in Olomouc, because it is connected also with one practical applications from the cartographic area. So as our motivation, we took the following issue that in many scientific and also application domains, we need to compare not only the attributes of some structure, but also the structured objects. We can imagine, for example, some structures of the graphs, networks, hierarchies. Also, our interests are concept lattices. And in this way, we have some distance functions by which we can quantify some similarity, dissimilarity. We can rank, cluster, or make some change detection. And many times in this structured data, some naive measures can ignore some internal structures. That's the reason why we started to work maybe on some more sophisticated distance functions. So we will use, just for a reminder, the notions of the metric, pseudometric, and similarity, because for some of the distance functions, we also proved that they are the metrics. In some of the functions, we obtain some counter examples. So these will be the three notions which we'll use in our presentation. And we also connected our results with the area of formal concept analysis, which is some specific method of data analysis in the group of the clustering. It's special because it produces big clusters. I will remind it in the next slide a little bit. But what is the main motivation to do also with formal concept analysis is the data can be represented in various forms. We can imagine data in the form of the documents, images, numbers, but also the sounds. But each of these data types can be in some way transformed or represented by also like numerical tables or data tables, because in documents, for example, we can use the methods of the embeddings, word embeddings, and to each word or sentence of the document, we can describe some vector. As well in the images, we can work with some pixels as the numbers. In the signals, we have again some vectors. So in this formal concept analysis, there are a lot of applications for different types of the data. And we will also stay in this field, theoretical and applicational. So to remind, we will work with these basic notions as well. This input object attribute table will be called the formal context. We can imagine it like the data table with the rows and the columns. In this field, we have just a binary relation, but we can also extend to the fuzzy as it will be introduced at the end of the presentation. Then we have the mappings, which are called derivation operators, which can be applied to subsets of the objects to produce some subsets of the attributes. And then we have the output of this method, which is the concept lattice, which is the ordered set of so-called big clusters. So in this, we can see the 5 clusters. It is really big clusters because first part of this cluster is subset of the object, and the second part of this cluster is a subset of the attributes. And this structure is called also concept lattice, like it was proposed in the formal concept analysis monograph of Ganter and Wille. And they also proved some basic properties in connection with algebraic notions like complete lattices, closure systems, closure operators. So some basic theorems hold that each formal context induces Galois connection. Each Galois connection induces a formal context, and this is something like chain of the theorems and lemmas which were proved at the beginning of this era. And our objective is the following. Now imagine that we have two data tables with the same objects, but the same objects can have two different groups of the attributes. So this is the first group of the attributes, and this is the second group of the attributes. So we can construct two formal contexts, two tables, and from these two tables we can construct two concept lattices. And now question is how to compare these two concept lattices, because now we have the same set of the objects, but two different sets of the attributes. So we started to make some review of the literature, and we found many interesting results in the literature, how can be compared two knowledge structures, for example, these concept lattices. Mainly Domenard and his co-author proposed several similarity or dissimilarity measures to compare concept lattices, but it was always based on the same set of objects and the same set of the attributes. Then we also found some Minkowski-like distance measures between concept lattices in the another work of the Bazin and Kahn, but it was again on the same sets of the objects and the attributes. Thus, our objective was the following, that existing lattice distances typically assume identical attribute sets, and we would like to propose some distance functions between closure systems, because concept lattice forms closure system, to compare concept lattices on the same set of objects, but with different set of attributes. And then also to use the proposed functions on the real data and to study the theoretical properties of such proposed distance functions. So at the beginning, we defined the important notions to our work. So we have taken some system of the subsets for some set S. Also, we denoted by these brackets the closure system on this system of the subsets. And we know that in formal concept analysis, the closure systems, we can construct both as the set of all extents, so the part of the big clusters, and set of the all intents, so from the attribute side. So our first definition was the following, that now imagine that we have two closure systems on some set, and we will denote the size of the smallest system of the subsets, which we need to add to the first system to be the superset of the second system. And the following function will describe this way in symmetrical way. So first, we will ask what we need to add to the first system to be the superset of the second, and on the other way, what we need to add to the second system to be the superset of the first system. We also proved that this function is a metric on the space of all closure system on this set S. This is the example. Imagine that we have the set S, just 0 and 1, and we have two systems of subsets. So from the first side, if we will take this system of the subsets, we just need to add 0 to obtain the superset of the second system. And on the other way, to the second system, we need to add the set of 1 to be the superset of A. And since we need to add just one element on one side and one element on the second side, the resulting distance is 2. But then we started to think that it is maybe not very simple, but some first proposal. So can we improve these distance functions by some maybe more fine-graded, fine level of the data? And we reminded that in the closure systems and concept lattices, we often use the notion of mid-irreducible elements, which can be, for example, explained that there are the elements which have just one upper neighbor in the concept lattice, for example, A, B, and C, in this way. And these mid-irreducible elements can be imagined like some core of the concept lattice or something like generator of this concept lattice. And then we just also proved some lemma which shows some connection between the set of the meet irreducible elements of the concept lattice and the closure system. But with the help of these meet irreducible elements, we defined the two alternative distance functions, which can be applied to comparison of two concept lattices with two different sets of the attributes. So again, imagine that we have two closure systems, and first we will define the cardinality in which we will compute the set of the meet irreducible elements of the second system and set minus the meet irreducible elements of the first system. It is again in the distance symmetric, so from one side and from the second. But then we had also the idea to create a distance function in which from the set of the meet irreducible elements, we will extract or we will make difference with the full elements of the concept lattice. Maybe again, it will be better visible on the example on the next slide, but I would just to remind that we've also proved that D1 is a metric, but D2 was not a metric. So this is again example. We have now 3 element set. We will construct 2 systems. From A, the set of the meet irreducible elements is the following 3 subsets. For B, we have 2 meet irreducible elements. And then we will compute again this set differences. From one side to the another, it is 2. From opposite way, it's 3. So first distance function will return number 5. And the second distance is not so much symmetric. So we are mixing the meet irreducible elements and all elements of the lattice. So we will start with this one, and we will do this one set minus A, and we will obtain just one element will remain. Then we proved the theorem about the comparison of these 3 distance functions, which we proposed, and we found the following inequality. Making some basic interpretation of these distance functions, we were thinking that the first distance, it is something like a minimal transformation between closure systems. It is very sensitive to some global structure of the system. It is more precise, but computationally more demanding. On the other hand, D1 is easier to compute. It is symmetric difference of meet irreducible generators, but it is less fine-grained. And this distance, number 2, it penalizes generators from one system not present in the other. And it is suitable when one system can be represented like some reference or some baseline. That's the reason why we propose it as well. But it was obtained some theoretical results. Professor Krajci also met Professor Boženilek from Palacký University at our scientific board at our university, and they spoke about their researches. And professor from University of Palacký in Olomouc proposed to use our results in the practical application. He has some private collection of the geographical maps, also historical, also from nowadays. And from this data, he extracted some binary coded map content table. We started to construct more concept lattices on this data and applied the distance functions which we proposed and started to compare the similarity or difference detection and so on. So that's just basic review of these industrial maps. It was 63 school atlases of the world. It was school atlases. It was based on some criteria of the selection. So most of the atlases were from the Czech Republic and Great Britain, but it was also some other countries included, and it was from different period of the time. So this is the example of the one atlas. It's a map of the industry of the Czechoslovakia from the mid-20th century. And as we found, these thematic maps are shaped not only by some cartographic conventions, but also by some educational, cultural, and the other influences by different countries, because in some it was emphasized heavy industry, in others some technological sectors or some environmental issues. And after extraction of the data, we obtained the following table in which we have a group of the attributes corresponding to industrial sectors, power plants and transport, energetics, and mineral resources. So that's our experiment in which we created 3 formal contexts and 3 concept lattices. So for each atlas, we generated first concept lattice from this group of the attributes, then from the second and the third. And we found the following way. This is the number of the elements in the concept lattice, and this is the number of the meet irreducible elements. So we can see some differentiations, but more for us, it was more interesting to produce these distance functions and their results. We implemented these functions in the Go programming language, and we obtained the following distances between these concept lattices. So, for example, the smallest distance was obtained between industrial sectors and energy infrastructure. It is this first row. And the largest was between energy infrastructure and mineral resources. But maybe it was natural. It was because in these mineral resources, it was the biggest number of the attributes, and also it was some diversity. And also these mineral resources are often presented as some separate geological layers. But then we started to think how to extend it to the fuzzy extension, because we know that in the fuzzy extension we have informal concept analysis, very nice results produced not only by Brusco and Fuentes González, Professor Bielohlavek, but also people who are here at the conference, Manolo Hedasiego, Joško Poč, Radek Haláš, and other started to fuzzify the formal concept analysis in different, not only theoretical, but also practical way. And this is maybe some comparison how it can be done in a fuzzy environment, because Krejci proposed the modified Rice-Sieve algorithm, which is also based on the distance functions, but in comparison with other novel results, it compares distance between 2 clusters, not between concept lattices, but just between the clusters by this Jacquard type distance. But if we would like to make the similar results for the fuzzy concept lattices, we have, for example, 2 possibilities. One approach is maybe to define some distances between corresponding fuzzy generators and aggregate them over the lattice. But for me, maybe the most friendly, and I like more the second choice of using alpha cuts from the fuzzy concepts, because alpha cuts was the topic which I firstly presented at this conference several years ago. So from that time, I like this topic. So with these alpha cuts, we can construct from fuzzy concept lattices the crisp lattices, and then combine them with using our proposed function. So as the conclusion, this distance can quantify how differently 2 crisp or fuzzy lattices organize knowledge under uncertainty. And finally, we would like to mention that beyond these industrial maps, we are currently working with a wide range of binary and fuzzy data sets from different domains. So we welcome collaboration with researchers who are interested in not only FCA methods, but also other methods to these types of the data sets from e-commerce, cybersecurity, maybe energetics, biomedical data. And nowadays, last year, we also made some national survey of programming skills of the students in Slovakia. More than 29,000 of the students produced solutions for 12 tasks. And we have, again, this data on which we are now working, and maybe trying to produce some paper for concepts conference in the September. And that concludes our presentation, and thank you for your attention.
Thank you very much, Lubo. Time for questions or comments?
Yes. If nobody else. It is very common in mathematics that when we want to compare something, we immediately think of distances. Yeah. And that triangle inequality is often difficult to justify. And I noticed, but I also mentioned in my lecture, that to develop aggregation theory further, we can look at alternative measures, which are still close. These are monometrics.
Okay.
Monometrics don't have a triangle inequality, but they preserve betweenness.
Oh.
So I was wondering, in your structure, since you have inclusion and so on, we could easily look at monometrics, and maybe your D2 is
Yes,
such
yes.
one.
Oh, thank you, thank you. Yes, yes, we will try to look at it because also Professor Krajci is very interested in these metric properties, and I will try to discuss with him this monometric and how to include it here, and to maybe make some joint cooperation with you, as we already spoke before.
Even on the
But-
metric side, what is
Okay.
very interesting, but this is old work of mine 20 years ago. If you have these similarity measures like the one you mentioned, but there are dozens of others, if you want to fuzzify them, probably people forgot those results, but it's very interesting that the T norm that you should be using has to satisfy some conditions that are coming from quantum mechanics.
Oh, that's
And only in that case, you can preserve the Fukasiewicz transitivity, which is actually the same as the triangle inequality in the inverse. So distance function means for 1 minus Fukasiewicz transitivity.
Oh, thank you very much for this excellent remark. And yes, yes, because you are right that we had some complications with this triangle inequality. So yes, yes, thank you very much.
Okay, any other question or comment? Then thank you again, Lubo.
Thank
for
you,
your
thank you.
presentation. So now it's time for the third presentation, and the speaker seems to be myself, because somehow Andre has been co-author two of these talks, but has managed not to be the presenter. Okay. So,
Presenting last time.
yes. Thank you. Well, I'm going to introduce a joint work with also Domingo Lopez from Malaga, Andre Kritlov, which is here from Košice, and Marek Reformat from the University of Alberta, Canada. The idea is, again, focused on a fuzzy version of formal concept analysis in with an intended application for inducing new properties somehow to complete missing or needed information in RDF graphs. The idea is to use some of the existing construction, existing tools in FCA, so that they help us to somehow complete this kind of graphs according to some needs and evidence given by experts. So the preliminary, I will go very fast because they are the same in the two previous talks. We will be talking about complete restricted lattice, and then we will consider the fuzzy context, objects, attributes, and an incidence relation. Here we are using a slightly different notation because we GMI came from German and it was not very mnemonic for us. And given an L fuzzy context, there were the derivation operators which allow to build the concepts. There are two versions actually, one antitone and one isotone. This can be renamed somehow rigorous and benevolent by reasons that we will comment later. And these are two different sets, pairs of concept forming operator. Each one generates one different concept lattice with some specific properties. And the idea is to use the notion of bonds to compose context. And this can be exemplified by considering the composition of graphs, bipartite graphs, because actually a formal context can be represented similarly in with the same kind of information as a bipartite graphs. Consider we have two of these graphs, which which are formal contexts. I said these are the objects, these are the attributes, and again, objects and attributes. Here, the question is that we are using the same set of attributes in both contexts. Then, one possibility to compose these two would be to consider this kind of connection, which means that this point is connected to this if it is possible to get to there by some path. We cannot connect this to this because from this it is not possible to go. It's quite easy. And that is the benevolent, and there is also the rigorous, which is much more strict in the sense that, for instance, here this cannot be connected to any of the other. Why? Because it is not possible to get there by using all the possible paths starting from here. It is possible to get there by using this, but not by using this. Okay? That is the main difference. This can be formalized in this manner. One is essentially the supremum or existential, and one is universal property. So there is a clear semantic distinction between the two ways of defining this composition. And now, what if we have really two different, completely separated contexts? That means we don't have a common set of attributes. Then the idea would be to require something which glue them together by using a third relation as I told before, as a glue. The idea would be more or less like this. We have two contexts, B1, A1, and A2, B2. In principle, we don't have this part of information. And here it is the extra information which could be provided by an expert. Okay, is there any relation between these two sets of attributes? And the expert would say, oh, yes, there is this one. Okay, as soon as we have this extra information, we somehow are able to apply the previous strategy and define the two possibilities, the benevolent and the existential and the universe. Okay. And the formal definition is given there like this. As you can remember, I didn't pay much attention, but these two schemas of construction are clearly resembling the previous ones. And now the idea is to study the theoretical properties of these compositions and then see what can be done from the practical point of view on the problem of RDF graphs. The first theoretical properties of the composition so that by using relational logic of the terminology and terminology of the relational theory, we can define much more easily the benevolent composition like this composition. R1 composite to the T and then the transpose of R2. And we can see that actually it is not a strange or ad hoc construction, but it can be easily represented within the algebra of fuzzy relations. Actually, it is connected to the theory of fuzzy relational questions in the sense that the rigorous construction is, in fact, the greatest solution of a relational equality. So provides optimal information. We can, again, say that it is not any heuristic, but it has also a practical interest in that it is maximally informative. And then also we have some properties concerning the dynamic behavior of the composition. That means there are some monotonicity related properties. Benevolent construction is order preserving, and the rigorous construction is order reversing. So this can be also later to justify the interpretability of the completion of the graphs that we will be showing later. And the final theoretical property that we introduce is the duality, because these two constructions, in fact, are not exactly one the dual of the other, but so-so. We have two different relations. The rigorous can be somehow like a double negation, kind of the Morgan dual or something. But interestingly, when reading the negation in the second component, we have to make here a reverse and then a transposition. So this also reveals two different additional semantic interpretations of these inferences, which somehow say us that one of these constructions, both under the rigorous bond, one can be interpreted as a kind of backward reasoning and the other as a forward chaining reasoning. And in this case, one would be more suitable for some tasks like validation, filtering, or the like in one case, or prediction, classification, etc. in the other case. Okay, and now back to the RDF property inference. The idea is, well, by the way, I didn't say anything about what our RDF graph is. I guess most of you would know. It's a graph with some labeling information, essentially. And the idea is, okay, well, we have a graph, and somehow we need to focus on one particular state and try to extract as much information as possible. The idea would be first contextualize the RDF graph. That means create the formal context so that we can apply the previous constructions. Then, additionally, the user should provide some information mapping, if needed, gluing these two pieces of data, and then apply the construction or either the benevolent or the rigorous bond, and finally introduce the information back in the RDF graph format. I did this very fast because now I will try to specify a little bit on a more specific example by using the standard example in this area as the reviewer assignment for program committee chairs. Assume that you are organizing a conference and you receive a number of papers, and then you have to start the reviewing process. What would be the best strategy? That each paper should be submitted to people which know well the topics of the papers. Then assume that we don't have exact information, but that this information can be extracted from the net, for instance. We can have access to DVLP or any other database system, and with this kind of structure. There is some work with some keywords, the publication type, and the author. And then we have information between each person and the keywords they are publishing on. And then it is assumed that if one author publishes something, that it should be because he knows well the idea. And then we have an assignment between authors. Should be these authors are intended to be the program committee members with a list of their topics, so to say. This can be seen like this. Betty knows about system, GUI, data, the like. On the other hand, we also have the submitted papers, and is submitted paper probably we are requiring the authors to specifically state which keywords, which topics they are focusing on. And then we have two contexts like this, a reviewer topic obtained before by using DVLP or something. Another context, papers and keywords, because we set the authors to formally put that in the submission. But what happens? That in many cases, the keywords and the topics are not exactly the same. Then, in that case, the program chairs should be able to map each topic with the keywords and the other way around. In this case, the program chair would be acting as the external expert. And by using this information, the final output would be to link, to assign reviewers to papers. That is essentially the idea. So we might have from the DVLP that this would be members of program committee, FSTA, Council Lattice, and the like, and then the authors state this kind of stuff. We need to infer a missing link here. That would be the third part of the composition, the gluing relation. And we can put like this. This obviously needs to be done not in a crisp manner, but in a fuzzy manner, right? We decided here to use quarter. Fuzzy FCA is exactly fuzzy FCA. It is related to concept lattice. It is related to distributed FCA, less associated to topic hierarchy, and the like. And then by using this information, we can compute the 2 bonds, the benevolent and the rigorous. The benevolent, the first one, generates much more entries than the rigorous. This is obvious. This is exactly the same what happened with the graphs. And here, this can be used, for instance, a reviewer or program committee U would be a very good reviewer for the paper 1 and paper B. From the benevolent interpretation would be the perfect one. So here in this case, we could infer these links, as I stated before, as saying that an ideal reviewer would be those used by using the rigorous. And then some other, for instance, X could be a potential good reviewer for the new publication C because of this. X, something like that. Okay? And the important thing is that all of this can be done from an explicit and auditable score, which can be explained. Why are you assigning this? Okay, all of this coming back to the computational problems or potential problems. What about the complexity? The complexity is a polynomial in the size of the input sets, so it escalates moderately well. But it is true that it is not intended to be used to complete a whole RDF graph, just some focus parts we are interested in. The role of the expert here is essential because otherwise we cannot put together the two contexts. And this means that well, somehow we can think about mixing or taking benefits from both the symbolic learning that we have been applying here, or statistical learning in order to find some other approaches or to combine them. Just to conclude, we have presented a formal framework for generating graded RDF properties by leveraging the mathematical theory of FCA with some other methods. The theoretical result provide a robust mathematical foundation for this, and for future work, we will study the semantic space of benevolent and rigorous extreme by incorporating some other construction like intermediate quantifiers, OWA operators, and the like, and try to develop some efficient algorithm for the adaptive inverse problems, that is, to find explanations for hypothesis generation. And finally, a more ambitious direction is to explore the dynamic bond composition, in which the external information can be learned directly, not taken from an expert. And that's all. Thank you very much. Okay, now it's, I don't know. We have some time for questions.
I have to give a comment here because in my slides, I went down memory lane. The very first FSTA I participated in 96. And the first lecture I ever gave was actually about these fuzzy relational equations, on which I wrote a 500-page PhD. So we know all about these relational equations or inequalities. So the one you present on the left, you say this is the greatest solution of some equation or inequality. If it solves, it's the greatest solution of the equality, but it is always the greatest of the inequality. Also, the second one, it's a smaller solution of another inequality, but we also know a lot about the other solutions. For instance, the second one is the union of minimal solutions. So I was wondering if it is interesting if you, and this is actually the Bandler-Kohout composition, which we should use here in this context because Kohout was from Czech Republic. If even smaller relations that build up, the biggest one, would be of use. Now you have the rigorous one, but that one can be further decomposed. Could it help in like the, now you want to set a reviewer, but there are some options you have no choice. And to find them first in the way to an efficient algorithm. I'm not sure if my question was clear.
That's a good food for thought. Please. I already knew that there were some other relations with the optimality and the like, but in principle, we were interested in closing this first step and find and use specifically those which could be directly interpreted in this kind of examples. You are right that, of course, by using this other representation as union of minimums, the like might provide extra information just in case in which you don't have enough information in order to provide the assignment. So would be good to think about that. Thank you. Any other comment or no? Then please send me again. Okay, now we are starting the fourth and last talk of this session. The speaker is Anna Pankowska. Here it's only two co-authors, but actually there are three more. And she would be talking about embedding similarity with fuzzy uncertainty in retrieval augmented generation. Oh, please.
Okay, hello. On behalf of my colleagues from Adam Mickiewicz University, I would like to present some preliminary work. There are no formulas in this presentation. I just want to share some ideas, some concepts, some dreams, maybe, how to benefit from fuzzy set theory in the area of LLMs and RAC. Okay, so I will skip just this basics about generative AI, and let us focus on LLMs and RAG architecture. RAG is a way to overcome some limitations of LLMs, like lack of up-to-date knowledge, limited trust. So we take embedded query. We have a vector database with the documents, and LLMs is preparing relevant documents to answer the query and to retrieve it to the to give it to the user. And a document is represented by embedding in such a way that similar documents, similar texts have embeddings that are close to each other. This closeness, this distance is calculated with cosine similarity. Well, obviously we do not, well, obviously or not, we do not represent this document by one embedding, but by one point. But this embedding, this point in multidimensional space is happen to represent the meaning of the text, but we currently divide this document into smaller parts, so-called chunks, and we calculate the embedding for each of this chunk. However, this embedding somehow summarizes or aggregates the meaning of the chunk. So if the text is complex, there is a possibility that we lost some information, we ignore some information from our experience. We observe that if we have some very strong, important sentence, and it can dominate the whole part, the whole chunk. So we can lost some niche information, some niche sentences that can be in this chunk. This is our first motivation to better represent the complexity of the text. All right, so let's see this figure. Here we calculated the embeddings of a text by adding consecutive sentences. And so we can see the shapes. They indicate that the meaning changes slightly. The meaning changes a little bit. So the embeddings are close to each other until there is one sentence that changes everything. The meaning has changed. There is a gap. There is a bigger distance between the embeddings. So there is a topic shift. And there are two conclusions from this visualization. The first one is that chunking that is sharp, that is static, that is arbitrary, is probably not the best way to divide the document. And the other one is another motivation, probably now the most important for us, is that we want to model the smooth change in meaning, because the meaning is changing, well, in some parts smoothly, and there is a well, the slightly only change in meanings, and sometimes rapidly. So probably the fuzzy modeling could be proper to model such change in meanings. Okay, so let us try the fuzzy perspective. As an example, we took some documents from Wikipedia describing Polish cities. Here we can see a part of a document describing Poznań, our city. And it can be seen as a fuzzy set, as a heat map of semantic meaning of this document. For each sentence, there's a color connected with it. The intensity of this color indicates the importance of the sentence. So this is one of the possible interpretation of the membership degree, probably not the only one, but now we use it. The importance of the sentence, like the amount of information, the amount of meaning. It is calculated in such a way that we take a sentence and we take a chunk that contains this sentence, and we calculate embeddings with and without this sentence. So, and we measure the distance between these two embeddings to see how the meaning has changed, and it indicates if the sentence was important for this chunk or more or less important. Okay. Okay. So another visualization of the same documents, actually. Here are on the X axis, there are indexes of sentences. On Y axis, we have the importance of the sentence. So, for example, we can observe that at the end of the paragraph, the sentences are less important, but there are also some peaks, some sentences that stand out from this document. So we overlay this figure with beginnings of the paragraph depicted here by the red lines, and we can see that these important sentences, sometimes they are at the beginning of the paragraph, but not always. So this is another evidence that chunking along paragraph headings, maybe it's not the best way to do it. So our next thought is to do better chunking, maybe do it in totally different way. We want to also analyze the entropy of the document. So this is the first try to see how the information, how the meaning concentrates in the document. And we can see that the biggest change in the meaning comes with this smaller, with the shorter chunks. So anyway, it's just, another motivation for us that this fuzzy perspective can give us a better insight into the characteristic of the document. So we can use it then to process better this document. Okay. Currently, because of the complexity of the meaning, of the semantics of the document, the common approach to retrieval is to divide it into two stages. So the first stage, a large amount of documents is retrieved to maximize the recall, not to miss any document that could potentially be relevant to the query. And then there is a second stage with ranking. And in this second stage, LLMs they choose 10 or so relevant documents that are give to the user, and this is the costly part, the computationally costly part. So what we want to do is, first of all, represent a document as a fuzzy set. It's just see it as a collection of fragments with different contribution to the meaning. If we have a document as a fuzzy set, then we can measure similarity between those documents, the distance between those documents. We want to propose a measure to the relevance of this document, of the query to the document in this fuzzy context. We would like to do better chunking, or maybe because now this chunking is like sharp and strict and static, maybe it's not necessary. Maybe we can model a chunk not as a point, but as a fuzzy point. So better to do this in a better way. We want to, first of all, model this change meaning. And finally, when we hope that it could help us to modify this retrieval phase to better choose the best documents in the first phase, in the first stage, and to reduce the necessity of this costly re-ranking phase. As you can see, there are more questions than answers, but we want to present it here, hoping that there are some of you interested in the subject, and we want to invite you to cooperate, to contribute to this project. And thank you very much.
Or question or comments?
It's difficult
Okay.
now. We hopefully hear some comments from.
I had can you go back to the example of a Postnam from the wiki?
Yeah.
Because you were commenting that the different levels of color were somehow related to the importance. How did you assign this importance? Was it something objectively or subjectively assigned?
Now it's objectively in the sense that we calculated with some algorithm to take a sentence, remove it from the text, and see if if there's a change in the meaning. We are using some of the known algorithms of embedding the text. So the text is embedded with and without this sentence. So you get some values. We measure that, and that's it. That's it. The bigger the distance, the more important the sentence is, because removing the sentence changes the meaning of the paragraph. As far as I know, we have different approaches to removing the sentence from the chunk. We remove it from the beginning of the chunk, from the end, from the middle. We just aggregating it, something like that. But it's just calculated with the distance between embeddings.
Yeah, but does it allow to make a pairwise comparison? Because somehow I can understand that you compute with or without, but how, for instance, this and this have the same importance? So, probably
It is possible, I think. It is computationally complex, really, because there's a lot of computation now. We want to somehow make it more efficient, but now it's really complex.
Any other questions? Yes.
Since you asked, since Irina is not here, you asked for interest in the topic. I would just like to refer to some work we did, which is maybe as an idea useful. So it's the topic of document set expansion. So now you start from one document, or how does it work? So I'll say what we solved. Suppose you have a number of documents. This is what I'm interested in, but I don't know how to describe what I really want. Just give me things that look like those three. And then the algorithm generates a few other ones. And you say, oh, no, this is not what I want. Oh, this is interesting. And you combine to the set and offer it again. This is not what you're interested in, but the algorithm at the same time generates a query. And the shorter the query, the more clear the concept is that you're looking for.
Okay.
And secondly, this is just a submitted paper. You look at the evolution, but your evolution is inside the document. We did it over time to see how topics come and go. Like in some time we have Wokism and all these notions that come and go, but they show similarities with things in the past. Like we have some similarities with the 30s now in the US happening. Like,
Okay.
you can look at trends in these documents, but all of those are based on very rough estimates. So you use a fuzzy set here. In our case, we model by B-splines and resample, because whatever we see is just a very rough portion. And especially now, which is one of my biggest concerns, sorry to make this a long question, is that if we are going to base this work or what we can find on the internet, half of the internet is already written by ChatGPT nowadays. So we are lost, doomed.
Yes,
There's no way to go back.
hopefully there is, but we can
I
see
think
it.
there's interesting things to be done.
Okay, thank you very much for your comment. I would like to get know these papers.
Okay, we still have some time for some extra question or comment. If not, let's thank again speaker. And this has been the last talk, so the session has finished. In a few minutes, the lunch will be open. Okay, thank you.